Okay. So, what have we gone through? Probably it sounds like I'm reviewing things a lot or kind of repeating myself a little bit. But after yesterday, you all know how to solve. So we can solve all second order linear homogeneous differential equations with constant coefficients. So in particular, if the characteristic polynomial has two distinct roots, so char poly has two distinct roots, what do solutions look like? What does the general solution look like?
We're having a hard time seeing your paper today.
The paper is blurry?
Yeah.
Huh. Did that help?
No, that
Not
might
really.
be worse.
I think it's an internet problem.
It might be an internet problem because things look clear from where I am. So it's possible that there's something going on. Let me make sure that everything else is closed so that my processor isn't burdened. Is any of this helping?
Yeah, it still looks pretty blurry on my screen.
Agreed.
I'm not exactly sure what to do since it looks clear on mine. So it's either an issue with my internet or, well, yeah, it's probably an issue with my internet. If I write bigger, would that help, do you think?
I think so.
Okay. So if the characteristic polynomial, oh man, this is going to be a disaster though. Is that legible?
Yeah, we can see that.
Yeah,
Okay. If the characteristic polynomial has two distinct roots, then what's the form of the solution?
You have y equals c1 e to the first root plus c2 e to the second root.
Yep. E to the first root times t, but yeah, you're right. Plus c2 e to the r2 times t, where r1 and r2 are roots of the characteristic polynomial. Is it still blurry? Like, is this stuff legible or not?
It looks
It
better
looks
for
a little
me.
better.
Yeah.
It's a little better?
Yeah.
Okay. I mean, you know, I have no idea what to do if it's an internet issue. Shoot. Okay. So this is if the characteristic polynomial has two distinct roots. If the characteristic polynomial has complex conjugate roots, what is the answer?
Using Euler's formula.
Yeah, exactly. You use Euler's formula. Euler's formula. So this is essentially you're going to get one solution that looks like e to the a plus bi t. And you're going to expand this as being equal to e to the a times cosine e to the at cosine of bt. This will give you one solution, and then e to the at sine of bt will give you the other solution. So our general solution looks like c1 e to the at cosine of bt plus c2 e to the at sine of bt. General solution. Still blurry, or are we doing okay?
That's
yeah,
okay.
it looks okay.
Okay. And now we know what to do with a repeated real root. Repeated real root. What do we get here for a general solution?
You get e to the RT and then some other function that we have to find.
So that is definitely the general thing that you should keep in your mind, but the general formulation is actually very explicit. It's actually going to be C1 e to the RT. We know that this is a root, right? Where R is the root of the characteristic polynomial, plus C2t e to the RT. So you're absolutely correct about how did we find this alternative function, but it turns out that for all differential equations with a degree 2 characteristic polynomial, where that characteristic polynomial has a repeated root, you're always going to get the same function out front, and it's just going to be a t. So C1 e to the RT plus C2t e to the RT. So these three general solutions to these kinds of second-order homogeneous linear differential equations are definitely things that you should be very familiar with and probably, I would say memorize, but you're kind of forced to memorize them just by using them so often on the homework.
Would on a test, could we just know that the general solution is whatever it is, so we can like do it that way, or do you need us to find it every time?
No, if you're asked to solve a second-order homogeneous linear differential equation, and you find its characteristic polynomial, and you tell me which of the three cases it's in, then you can just write down the general solution.
All right, thanks.
Yep. Okay. But of course, a very good point was made. The idea for how we found this general solution was as follows. We have one obvious solution, namely e to the RT, right? If R is a root of the polynomial, then e to the RT has got to be a solution to the differential equation. To find the second solution, we examined u of t times our first solution, e to the RT. And we plugged this into the differential equation and produced a differential equation for u that said, whenever u satisfies such and such differential equation, then this whole thing will be a solution, right? We basically asked, when is this solution? And the answer was, this is going to be a solution. So answer, u of t times e to the RT is a solution of a y double prime plus by prime plus cy is equal to 0 whenever u double prime of t is equal to 0, right? Do you remember this calculation that we arrived at yesterday?
Yeah.
Right, but the second derivative of u being 0 tells us immediately what the general form of u has to be. This implies that u of t is equal to c1t plus c2. So thus, we get c1t e to the RT plus C2 e to the RT as our general solution. Okay, this is all just review from stuff that we did yesterday. So I kind of want to make sure that we go over this another time just so that things are clear and we kind of see the final answer to this problem. Does anyone have any questions about anything at this point? Okay. As a slight expansion before we move on to non-homogeneous differential equations, let me remark that a more general notion, slightly more general notion, and it's called reduction of order. And this is, reduction of order is going to be essentially using the exact same technique that we used up here to find a second solution. Except now we're not going to be limiting ourselves to second order homogeneous linear differential equations with constant coefficients. Now we can take arbitrary coefficients. So suppose that y1 is a solution to y double prime plus p of t y prime plus q of t y is equal to 0. In other words, y1 is a solution to this second order linear homogeneous differential equation that is more general than just having constants out front. We want to find when u of t times y1 of t is also a solution. So this is exactly what we were doing yesterday. We're just expanding the kinds of differential equations that we're thinking about. And the answer is, this is pretty simple. All that we need to do is plug in this function into this expression. So we need to take second derivatives here, first derivatives here, and so on. And we did this yesterday, but it's not a bad idea to repeat it. So what's the second derivative of this product of functions? Plug this into diffie-q. What do we get? Well, the second derivative of this function is going to look like u double prime of t times y1 of t, right? Plus, I think I should get 2 u prime of t y1 prime of t plus u of t y1 double prime of t. That should be this thing. Plus p of t times the first derivative of this, which is going to be u prime of t y1 of t plus u of t y1 prime of t, plus q of t times u of t y1 of t. Is everyone happy with this? Probably, because you all know how to take derivatives. So we've got this gigantic expression, and we'd like to collect terms. So first of all, let's collect all the terms that only involve a first derivative of u. So what we've got over here is I'm going to be able to rewrite this whole thing as u of t times, I've got a y1q, or a qy1. I've got a p of t times y1 prime. And I've got a y1 double prime. I've just collected all the terms that only involve u of t. And now if I collect the other terms, I'm going to have the terms involving u prime. And I'm going to get a 2 y1 prime, shoot, I don't have space, plus py1. And then if I collect all the terms that involve a u double prime, I just get u double prime times y1. All this is going to be equal to 0. This is essentially just a repeat of the calculation that we did yesterday, so I am being a little bit speedy, but is everyone okay with what I'm doing right now? Anyone have any? Sorry, can you say that again?
Yeah, on the very far left-hand side, does that say u double prime?
Yes, this is u double prime. This is the second derivative of u and no derivatives on the y. And it's just, yeah, what I get from separating out terms in this big, applying the differential operator associated to this differential equation to this function. Now, what is y double prime plus p of y prime plus q of y1?
0.
Yeah, this is 0 because y1 is assumed to be a solution. So what we get is u double prime times y1 plus u prime of 2y1 prime plus py1 is equal to 0. And as I remarked last time, what is this?
First order differential
This
equation.
is a first order linear diffie q for u prime. And for first order linear differential equations, we know that we can write down precise solutions. Maybe they involve the first fundamental theorem of calculus, so we have to write it in terms of an integral, but we can write down an explicit solution for u prime. And then once we have an explicit solution for u prime, we can take the antiderivative and explicitly find u. So thus, so can explicitly solve for u prime of t, and then take antiderivatives and have explicit expressions for u. So this is why it's called reduction of order. What we're trying to solve here is a second order linear homogeneous differential equation for y. When we make this substitution and we start examining u of t times y1 of t, we end up with a more simple differential equation in terms of u. You could think of this either as a second order linear differential equation for u, which doesn't have any u term. It's only involving u double prime and u prime, or, which amounts to the same thing, this is a first order linear differential equation for u prime. So we can actually solve a first order linear differential equation, and then we can take an antiderivative and explicitly find, more or less, maybe not in terms of elementary functions, but as explicitly as could be hoped for, we can find the function u such that u times y of t is also a solution, and thus produce our whole family of solutions.
We wouldn't have a means of finding y1 yet, right?
That's correct. For this general differential equation, if these aren't constants, and this isn't of the form of an Euler equation, which is a change of coordinates away from being a constant, then you have no way a priori of finding what y1 is. In particular, in this next example that I would like for y'all to work out, you're given one solution and you're asked to find a family of solutions. Any further questions? I think this does become more reasonable with an example, so let's do an example. So, example. say that you're given the second order linear differential equation t squared y double prime minus 4t y prime plus 6y is equal to 0, and you're given the solution t squared, or say, let me write it, y1 is equal to t squared. So one can check that y1 being equal to t squared satisfies this differential equation. And so what we should do is we should find a second solution or find a family of solutions. Does everyone understand what the kind of plan of attack is, or what I should do first?
Yeah, for this example though, wouldn't it just, like generally speaking, make more sense to approach it with Euler's equation?
Yes, that's true. This is one of the Euler's equation ones, and so we could do that. But we can also do it by examining this, multiplying the solution by a function. That's a very good point, though. This could be done with the Euler method. Okay, so first of all, I think that we should start by getting this equation in the right form. So first, we want to write this as y double prime minus 4 over t y prime plus 6 over t squared y being equal to 0. Right? And then from the previous page, well, okay, so now consider u of t times t squared. And what we want to do is we want to plug this into this equation and see what we obtain. So also remember, you don't actually need to do the full computation. You can also just use the expression that we found here, namely u double prime times your solution plus u prime times 2y1 prime plus py1 prime is going to be equal to 0. So what we know is that u double prime of t times y1, which is in this case t squared, plus u prime of t times, here I take 2 times the first derivative of the first solution, so 2 times 2t, plus, and now I look at p, my function here, plus minus 4t times y1, or sorry, not here, here, minus 4 over t times t squared. This is supposed to be 0. Do we agree that this is, well, let me just write it. This is exactly the equation that we found on the last page, which is u double prime times y1 plus u prime times 2 y1 prime plus py being equal to 0. I'm just plugging in that here.
Wait, is there an extra parentheses at the end of that equation, right around where it says like t squared? Oh, okay, there we go.
Okay. So what do we get out of this differential equation?
You just get u double prime is equal to 0.
Yeah, we actually get u double prime of t times t squared is equal to 0. And then if we assume that t is not equal to 0, so we're looking away from 0, then we get u double prime of t being equal to 0. And you all know exactly how to solve for u when u double prime is equal to 0. What does this imply?
U is equal to like C1 times T plus C2.
Yeah, u is equal to C1t plus C2. Thus, we get that the general solution is C1 t cubed plus C2 t squared.
So I'm sorry, where does that come from?
Where does what come from?
Sorry, I didn't understand that jump to this general solution.
Okay, so what I've done here is I found the general solution to this second order differential equation, which says I'm looking for a function of t whose second derivative is 0.
Oh wait, no, I get it now. I'm sorry. Yeah, that's u. You multiplied everything by t squared for y2.
Yeah, exactly. This is exactly the product of u times y1, where y1 is equal to t squared. Yep.
Right. Thank you.
So the what is the point here? I suppose the real point of this discussion of reduction of order is to point out that, naive though it may be, this is a more general procedure that is not a bad idea to try. If you've got a differential equation and you've got one solution, a reasonable way to try to obtain further solutions is multiply by some unknown function. And then if you plug that new product of functions into your differential equation, perhaps you get a different differential equation in terms of u or u prime that you can actually solve. And in that way, you can try to produce general solutions out of one solution to your differential equation. Any questions on what we did here? Yes? No?
So on an exam, in a situation like this where you could use the Euler's method, would you specify which one you wanted?
Yeah, if I want to see you use a particular method, I'll tell you. And if I just gave you this problem with nothing said, then I'd accept either approach.
Thanks.
Yep. Okay, are we ready to move on? I'll take that as a yes.
Yeah.
Thank you. Okay, so now let's begin into 3.5. So section 3.5 represents a kind of interesting and important jump. This whole time, we've now been in chapter 3 for like a whole week. We've been discussing nothing but second order linear homogeneous differential equations, most of them just with constant coefficients. So now what we add back into the mix is we're now going to examine non-homogeneous differential equations. But still, of course, second order linear. Non-homogeneous second order linear differential equations. So there's one point that I kind of harped on about in terms of second order linear differential equations. And there's some very nice property about their solutions that is kind of very important to remember. Can anyone tell me what that property is?
You can always find the interval on which there exists a solution.
So that is actually true both of the homogeneous and the non-homogeneous case. Really, that's a property of being a linear differential equation. It's the nonlinearity that messes with your domains of definition for your solutions. So we've added back, so maybe in terms of expressions, let me remind you what non-homogeneous means. It means now we're examining things of the form y double prime plus p of t y prime plus q of t y is equal to g of t. Remember that existence and uniqueness for this is pretty much the same as existence and uniqueness for 0. The only thing I need to remember is I need to factor in when g is continuous, or the domains on which g is continuous. But from the perspective of the existence and uniqueness theorem, whether this is g or whether this is 0 doesn't make much of a difference. In other words, homogeneous is L of y is equal to 0 is a solution, where non-homogeneous is L of y is equal to g of t is a solution. So no one else has said the magical words, but solutions to a homogeneous second order linear form of vector space. That is, when you add two solutions, it's still a solution. And when you multiply a solution by a constant, then it remains a solution. Notice that those properties can no longer hold for a non-homogeneous differential equation, because if if L of y1 is equal to g of t, and L of y2 is equal to g of t, then what is L of y1 plus y2?
Two g of t?
Yeah, 2g of t. Okay, so what we should kind of conclude from this is that, first of all, having your solutions be a vector space is a really nice property, and we're sad to leave it behind. But on the other hand, this rule for what happens to solutions as you add them isn't so bad, right? This is like it's true that this is no longer a vector space, but maybe this is manageable. And what I'll write down as our next theorem is that indeed it is manageable. So let me discuss what properties we get for solutions to non-homogeneous differential equations. Okay. Fundamental result. So what I'll write for the solution to a non-homogeneous differential equation is usually like L of yi being equal to g of t. And this you should take to mean y double prime plus p of ty prime plus q of ty is equal to g of t. So first, if y1 and y2 are solutions to L of yi is equal to g of t, namely these are solutions to the non-homogeneous differential equation, then y1 minus y2 is a solution to the homogeneous part, to the associated homogeneous diffie-q L of y is equal to 0. So to every non-homogeneous differential equation, linear differential equation, we have an associated homogeneous differential equation by just forgetting about the g of t, right? You can just say, take the left-hand side, the linear differential operator piece, and just set it equal to 0. What I'm saying is if you have two solutions to this thing, then their difference is a solution to the associated homogeneous differential equation. Moreover, the second part, if y1 and y2, here I'm using little y's, form a fundamental system of the homogeneous piece for L of y is equal to 0, then we can express this difference, y1 minus y2 is equal to c1 y1 plus c2 y2. So the second part is pretty much obvious once we show the first part, right? The first part says, given two solutions to the non-homogeneous differential equation, we can produce out of those two solutions a solution to the homogeneous part. And then the second comment is that any solution to the homogeneous part is going to be able to be written as a linear combination of a fundamental system of solutions. So what we're doing here is we're kind of tying solutions to the non-homogeneous differential equation back to solutions to the homogeneous equation. We want to kind of use all the things we know about the homogeneous differential equation in terms of our understanding of the non-homogeneous one. Any questions just about this, this result?
Wait, what are the difference between the big Y's and the little Y's?
The big Y's are supposed to be solutions to the non-homogeneous. So that means when I apply the differential, so remember that, so here, L of a function phi is equal to phi double prime plus P of t phi prime plus Q of t phi. So when I say big Y1 and big Y2, or capital Y1 and capital Y2 are solutions to this, what I mean is that when I apply this differential operator, I get back G of t. So these are solutions to this thing being equal to G of t.
Gotcha.
Whereas little y's, when I apply this differential operator, I get 0. Is that clear?
Yep, thank you.
Any other questions? Okay, the proof is very simple. Let's consider L of y1 minus y2, capitals. Well, we know about differential operators, that they act linearly. So this is the same as L of y1 plus L of negative y2, which is the same thing as L of capital Y1 minus L of Y2. And this is just essentially because differential operators, or D, the derivative, acts linearly. The derivative of a sum is the sum of the derivatives, and the derivative of a constant times a function is equal to the constant times the derivative of the function. That just means that it's being approached linearly, or that the differential operator D is linear. Okay, but what is L of Y1 minus L of Y2?
G of t minus G of t.
Yeah. This is g of t minus g of t, which is equal to 0. This is the proof that the difference of solutions to the non-homogeneous piece gives a solution to the homogeneous piece, because the differential operator applied to this function is 0. Right? Is it clear what I did here?
Yeah, I think so.
Yes.
Great. Excellent. I'm happy to hear it. And then the second part follows. We already know that essentially by definition, if y1 and y2 form a fundamental system, then every solution to this homogeneous differential equation can be written in terms of a linear combination of the fundamental systems. So we get exactly this. y1 minus y2 must be equal to some c1 little y1 plus c2 little y2 for some constants c1 and c2. For any pair y1 and y2 that solve the non-homogeneous differential equation. Okay? Great. So now we come to a very nice theorem, which tells us that everything is okay, more or less. Solutions to the non-homogeneous diffq L of phi is equal to g of t can be written as y is equal to c1 y1 plus c2 y2 plus big Y of t, where y1 and y2 are a fundamental system for L of phi is equal to 0, and y of t is any solution to L of y is equal to g of t. So essentially what this is saying is that in order to write any solution to the non-homogeneous differential equation, all you need is a fundamental system from the for the homogeneous piece, and then any solution that works. So first of all, we should check that indeed expressions like this do form a solution, but this is clear. So 1, show that these are solutions. But this is easy. What is L of c1 y1 plus c2 y2 plus y? What can we do with L? How does it play with these functions? What did I do up here?
You applied it to each piece separately?
That's right. Remember that this L is some combination of the differential operator derivative, d, and multiplication by functions, and that's a linear operation. So L of some sum of things is going to be equal to L of c1 y1 plus L of c2 y2 plus L of y. What's L of c1 y1? Remember that y1 and y2 are a fundamental system for the homogeneous part of this differential equation.
Is it just 0?
Yep, this is just 0. What about this one?
0.
Also 0. And what about this one?
G of t.
Yep, G of t, exactly. So we know that anytime that we write out any function that has this form, where I've got, this part looks like a solution to the homogeneous piece, and y is any solution to L of y is equal to G of t, then that is a solution to L of y is equal to G of t. That part is kind of clear. It's okay. What I'm showing is that these things are indeed solutions to the second order linear non-homogeneous differential equations. What should I show next? What is the other thing that we need to prove? Someone's got to give me something. What were we able to do with fundamental systems of solutions for homogeneous differential equations? Once we had a fundamental system, are there any solutions which are not written as a linear combination of the fundamental system?
No.
That's correct. The answer is no. Every single solution to the differential equation can be written in terms of our fundamental system. We need to prove that here as well. All solutions to this differential equation, L of y is equal to G of t, can be written in this form. We want to show that this is the, or a general family. Well, this is a parameterization of the general family of solutions to L of y is equal to G of t. Okay? So we need to show that any y, say y1, such that L of y1 is equal to G of t, can be written as C1 y1 plus C2 y2 plus y, right? We want to show that all of them are of this shape. Do we agree that this is what we need to show?
Yes.
Yeah.
Okay, but this is just a consequence of the theorem that we had before. We know that y1 minus y0, let's call this thing, what do I want to say? I know, let's pick particular numbers here. So let's find some solution that looks like this. So we know, what do I want to do here? Let's pick constants, a1 and a2, so that a1 y1 plus a2 y2 plus y is a fixed solution, is a particular solution to L of y is equal to G of t. Let's call this y0. Given any solution y1 such that L of y1 is equal to G of t, by the theorem, so by theorem on previous page, y1 minus y0 can be written as what?
G of t?
Yeah, this, not quite G of t. These are two solutions to the non-homogeneous differential equation. So the difference is going to be a solution to the
homogeneous. Zero.
Which means that I can write this in terms of the fundamental system. So this is going to be equal to some b1 y1 plus b2 y2, right? So now y1 is going to be equal to b1 y1 plus b2 y2 plus y0. And y0 is just equal to this thing. So this is equal to a1 plus b1 y1 plus a2 plus b2 times y2 plus y. So what I've shown here is that given any solution y1 to L of y1 is equal to g of t, then I can express y1 as some coefficients times my fundamental system for the homogeneous part plus a given fixed solution to L of y is equal to g of t. Are there any questions about what I've shown here? Any confusion? I feel like maybe I was kind of confusing with this. Anyone confused?
This is just to confirm. So the y0 is like the y in that is just a non-homogeneous solution?
Yes. So this y and this y0 are two different solutions to the non-homogeneous differential equation. So if I apply L to y, I'll get g of t. And if I apply L to y0, these go to 0, and I'll get g of t as well.
Okay, that makes sense. Thank you.
Yeah, sure. So the point here to find the general solution to L of y is equal to g of t for L second order linear differential operator. We need two pieces of information. One is we need the fundamental system for L of y is equal to 0. Two, we need just one solution to L of y is equal to g of t. Then 3, general solution is c1 y1 plus c2 y2 plus big Y. So you see we've actually linked these solutions to the non-homogeneous differential equation very tightly to the solutions to the homogeneous differential equation. They're only different by some solution to the non-homogeneous differential equation, and then all of them look like this. Or in other words, the way to go back and forth between solutions to the homogeneous and solutions to the non-homogeneous is just to add any solution to the non-homogeneous. This clear? It's unfortunate that I have to take your silence for a yes, but it'll do. I understand. Let's do some examples. Examples are always great. So We already know how to do part 1 to the best of our knowledge, which means we can't do it in general, but when L is given in terms of constant coefficients in front of y double prime and y prime and y, then we have exact precise solutions. So in a certain sense, we have done as much as we can do for 1, right? Like any other techniques to solve more general second order linear differential equations are going to involve more ideas, so to speak. So the part of the problem that we're now going to consider is, how do I find one solution to L of y is equal to g of t when L of y is equal to second order linear differential operator? So there are 2 methods of finding a specific solution y to L of y is equal to g of t. And the first solution, which gets this big fancy name called undetermined coefficients, is literally the most naive and basic thing that you could possibly try. And the answer is yes. We're just going to try to guess solutions to this second order linear differential equation and see what coefficients need to appear so that it works out. It's like really funny to me. Hopefully it'll be funny to you after we do some examples. Okay. So as an example, let's try to find a specific solution to y double prime minus 2y prime minus 3y is equal to 3e to the 2t. So first of all, we already know how to solve the homogeneous part of this differential equation. So what we're really after is, let's try to find a solution. And here is the method of undetermined coefficients, of derivatives that we need to take. And this messy combination of derivatives and sums of derivatives needs to be 3e to the 2t. A very naive guess is that, well, maybe I should look for something that looks like e to the 2t. Let's guess that a particular solution looks like a times e to the 2t, where we're not going to decide what this constant a should be yet. Once again, I want to emphasize, this is like the most naive possible thing. Like, I'm looking for a solution to the second order differential equation that looks like an exponential. Well, maybe I'll just try an exponential and see if that works. But it turns out that this is going to work. So why don't you figure out what happens if we plug in this into this equation as an exercise? It's quite easy. In other words, I'm asking for L of a e to the 2t is equal to what?
Three e to the 2t.
Yeah. So when let me just do it step by step. When I take the second derivative here, I get 4a e to the 2t minus 2 times the first derivative, so 2a to the e to the 2t. minus 3 times a e to the 2t. And this whole thing is going to be a minus 3 a e to the 2t. Do you agree?
Yeah.
Yeah.
Yeah, I should have a minus in front. And now I'm just saying, what should a be? So that, like, can I force negative 3a e to the 2t, which is the left-hand side, to be equal to 3e to the 2t, which is the right-hand side, by a choice of a? And the answer is yes.
Yeah, you just make it like negative.
Yeah. If a is equal to negative 1, then they are equal. So negative e to the 2t is a particular solution, or a particular solution. We'll call it capital Y to L of y is equal to g of t, or in this case, 3e to the 2t. Where here L is d squared minus 2d minus 3. Okay, so now that I have a particular solution, what is the general solution to this differential equation? Now I need to go back and find the general solution to the homogeneous part. What are the roots of the characteristic polynomial of this differential equation?
One and two.
I don't think 1 and 2 will work because their product will not be 3.
3 and negative 1.
Yeah, 3 and negative 1 will work. So roots of the, is there, oh, move it out. Is that what you were asking? So roots of the characteristic poly of homogeneous piece are 3 and negative 1. So the general solution is C1 e to the negative t plus C2 e to the 3t plus negative e to the 2t. This is, well, I already wrote y for something, but I'll abuse notation and say this is the general solution. And this kind of makes sense, right? Because you know that for any constants that I plug in here, the derivative of this whole thing will always be g of t, because the derivative of this chunk will be 0. Not the derivative, the differential operator applied to this chunk will be 0, and the differential operator applied to this chunk will be g of t. And then the only thing you have to do is you have to achieve different initial conditions. And you can achieve any initial condition in terms of the position at t0, or the value of y at t0, and the value of the derivative at t0, just by playing around with these two coefficients. So it makes sense that this is a general solution. Any questions about this? So the method of undetermined coefficients when g of t is an exponential function is guess that it's an exponential function with the same coefficient in the exponent.
This could just be me, but did we switch the signs of the roots?
Well, let's take a look. Let's do this carefully. So this characteristic polynomial is going to be x squared minus 2x minus 3. And so this is going to factor as x minus 3 times x plus 1.
Right, I see it now.
And then now the roots are going to be 3 and negative 1. Yeah, I was going a little fast, but that's a good question. Any other questions? Well, in that case, let's do another. Let's see. Let me do the following. Find the general solution to y double prime minus y prime minus 2y is equal to negative 2t plus 4t squared. Okay. In keeping with the most naive guesses possible, there are 3 parts to this problem. First part is to find the fundamental set of solutions, or the fundamental system of solutions to the homogeneous piece. I trust that you'll be able to do that. We're going to do the second part first. We need to find a specific solution to this differential equation, where after taking some combination of derivatives and adding things together, I get a polynomial of degree 2. What should my naive guess for a specific solution be?
Some polynomial of degree 2.
Yeah, let's try a polynomial of degree 2. Exactly. So what I would like for you to do is solve this. Y double prime minus y prime minus 2y is equal to negative 2t plus 4t squared. So maybe the first thing that I should comment is that we probably, so for our naive guess at a particular solution, 1, we should guess a polynomial. Because sometimes in math, you shouldn't be creative and you should just do the most simple thing. The second comment is, do I need to consider polynomials of degree greater than 2?
You could if you wanted to.
I could if I wanted to, but there's an easy way to see that those will never be the answer. And that is because, let's say that I had a polynomial in t of degree 3. What's the highest degree that will appear after I take 2 derivatives?
1,
Highest derivative that'll appear after 1 derivative?
2.
And then I'll get a degree 3 term in y here. So the point is, nothing in these 2 terms will ever cancel with the coefficient in front of the degree 3 term here. In other words, that would mean I should expect a degree 3 term in the answer. But there's no degree 3 term here, so there shouldn't be a degree 3 term here in the y term. Does that make sense?
Yeah.
Yeah.
Right. Basically, there'd be nothing to cancel with a t cubed or a t to the 4th or a t to the 5th. Like whatever the highest degree of t that you guess for y, it won't be able to go away. So we should only consider polynomials of degree 2 or same degree as g of t, if g of t is a polynomial. So in other words, what you should consider is a polynomial y is equal to a plus, or let's say a t squared plus bt plus c. So I've helped you out on the guess, but why don't you find a specific solution to this differential equation now? Also, has the blurriness gone away, or is that still an issue?
No,
the
it's clear
blurriness-
now.
Looks
Yeah,
good.
that's good.
Okay, great. Maybe all my roommates were downloading gigantic files simultaneously. Anyone unclear about how to begin or how to proceed from where I left you? Happy to hear it. How are y'all doing?
Good.
Right. Okay, so let me just kind of get started on this. So all I'm going to do is I'm just going to plug in this expression into the left-hand side. So if I take second derivatives, I'm just going to be left with c, I believe. No, sorry. I'm going to be left with 2a, right? Taking second derivative is the only thing that survives is this piece. 2a minus, if I take first derivatives, I get 2at plus b, minus 2 times, and then I just plug in the whole thing, at squared plus bt plus c. And this whole thing is supposed to be equal to negative 2t plus 4t squared. Well, it's very obvious what a has to be now, right? There's only one term that maybe I should split things up, and so I collect terms with the same power of t. So I get negative 2at squared. Let me collect all the b terms, minus 2a, so plus negative 2a minus 2b times t, plus 2a minus b minus 2c, and that's going to be equal to negative 2t plus 4t squared. So now things become easy to solve, right? Negative 2a has to be equal to 4, so a has to be equal to negative 2. That makes this term easy to solve for. Negative 2a is just 4, so negative 2a minus 2b being equal to negative 2 implies that I've got 4 minus 2b is equal to negative 2, or in other words, b is equal to 3.
Are you able to move the paper up a bit?
Oh, I'm sorry, yeah.
Thanks.
Is this what y'all got?
Yeah.
And then lastly, if I know a, b, and c, then 2a minus b minus 2c is equal to -4 minus 3 minus 2c being equal to 0. So I get that c is equal to 7/2. No, -7/2. Yeah. Y'all in agreement?
Yeah.
So a specific solution I'll call it, what should I call it? Y1. Capital Y1 is equal to -2 t squared plus 3t minus 7/2. And now what is the general solution to this whole differential equation? Sorry, I can't really fit both onto the thing, but what's the fundamental system of solutions to this homogeneous part of this differential equation?
C1 e to the -t plus C2 e to the 2t.
C1 e to the -t plus C2 e to the 2t?
Yeah.
And then plus this big thing. -2t squared plus 3t minus 7/2. This y is the general solution to the differential equation. I add the general solution to the homogeneous piece plus the specific solution that I found. Is this okay?
Could you move the paper back down a little?
You mean up a little or down?
Yeah, thank you.
Yep. Okay. The last one that I would have y'all practice is essentially the last nice case where you can just guess and it ends up working out. What are some functions that are almost two periodic in terms of their derivatives? That means when I take their second derivative, I get back something that looks pretty much like the original function.
Sine and cosine?
Yeah, sines and cosines. Those are going to be the last things that we can do this kind of naive guessing with. So as our final guess, or as our final example, what you should consider is y double prime plus 2y prime is equal to 3 plus 4 sine of 2t. So first of all, maybe let's do this in order this time. What is the general solution to the homogeneous piece of this differential equation?
Zero, -2.
The roots of the characteristic polynomial of the homogeneous piece are 0 and -2. So the general solution to homogeneous piece is C1 e to the 0t, or C1, plus C2 e to the -2t, which is equal to C1 plus C2 e to the -2t. Right? There's no issue with 0 being a root of the polynomial. It just means that constants are solutions to this homogeneous piece. That makes plenty of sense. It's obvious that constants will always be solutions to differential equations where you don't have a y term, where you only have things in terms of derivatives, because every time you take even one derivative of a constant, it just goes to 0. So obviously constants are solutions to the homogeneous piece of this differential equation, right? These are the solutions to the homogeneous piece. The second thing that we need to do is we need to find an explicit solution. What should our guess be? Actually, now I want to make something else clear as well. Really, what we have going on here are like two separate pieces to the g of t. In other words, what I want to do here is I want to write g of t is equal to g1 of t plus g2 of t, where g1 is going to be equal to 3, and g2 of t is going to be equal to 4 sine of 2t. The point is that I can kind of treat these things separately, in the sense that if I find a specific solution to L of y is equal to 3, and so L of y1 is equal to 3, and L of y2 is equal to 4 sine of t, or of 2t, then what is L of y1 plus y2?
G of t.
Yeah, g of t. 3 plus 4 sine of 2t is equal to g of t. So to solve this problem, the first step is to find the general solution to the homogeneous piece. The next is to find two specific solutions, one to y double prime plus 2y prime is equal to 3, and the other to y double prime plus 2y prime is equal to 4 sine of t. We need to kind of find two distinct solutions. Okay. Let's find a distinct solution, or a specific solution to y double prime plus 2y prime is equal to 4 sine of 2t. What should I guess as a naive guess for y?
Something like a sine of 2t.
Something like a sine of 2t would be very good, and that's part of what we should guess. But remember that if we start off with sines, we're going to get cosines automatically. In particular, if I start off with a sine, then I'm automatically going to get a cosine term here. And there's no cosine term here, which means I'm going to run into trouble. Because if there's no cosine term here, I'm going to need the coefficient in front of sine of 2t to be 0, but then that won't be a solution. So my naive guess should involve both sines and cosines, since immediately when I start taking derivatives, I'm going to have both sines and cosines appear. So in this case, my slightly less naive guess should be y is equal to a sine of 2t plus b cosine of 2t. And it turns out that using this guess, if you have a trig function that's just in terms of sines and cosines, using a function in terms of sines and cosines on a second order linear derivative will generally get you the answer that you're looking for. So there are 3 minutes left. Maybe I'll just finish this problem off next time. That seems reasonable. Okay, with that being said, thanks for class today. I hope everyone stays safe as you're going forward. There are a lot of people who are going to talk to me about tests today, I believe starting around 2. So I'll just set up this exact same Zoom and then do breakout rooms where I chat with you at the correct time. So if you have a scheduled meeting to talk with me about your test, just hop onto the exact same Zoom meeting and we'll be able to chat about your tests. And is that all? Yeah. See y'all tomorrow. Have a nice afternoon.
Thank you.
Thank you.
Thank
you.
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 Oh, and I'll do office hours at like 1:05 if anyone has questions. Hey y'all, what's up?
Hi.
How you doing?
I'm doing good. How are you?
Doing all right.
I just have a quick question about the homework in 3.2.
Okay.
I don't know, sorry. Yeah, I think it's 3.2. Would you like me to share the screen? That would be easier.
Yeah, let me make that available. Okay, you should have an option.
Okay, it's just this question, and I'm having problems with, I guess, the strategy to find GFT once you know one of them and you know the run stain.
Mhm.
Like,
So how did we first define the Wronskian?
well, it's just a determinant of like t and its derivative, and then g of t and its derivative. But
Right.
then, so I tried doing that, but I just can't seem to find g of t once I try to like multiply it out. Like, do I have to guess what g of t is?
Well, I take the determinants of t1, g of t, and g prime of t. I'm just writing for myself right now. And that's going to be equal to t, g prime of t, minus g of t being equal to 0, right? Is this a differential equation that you recognize?
Oh, is it first linear?
This is a first order linear if we divide by t. This is g prime of t minus 1 over t g of t being equal to 0. This is a first order linear.
Oh, okay, that makes more sense.
Yeah.
All right, thank you so much.
Yeah, of course.
Let me stop sharing.
I just had a question not really related to the class again.
Okay.
But
yeah, sure.
kind of, I guess. I was reading over the notes and everything. And so we came pretty close to like providing a proof for Euler's identity. I was wondering, I get mathematically why it's true, like from everything we did.
Uh-huh.
I was wondering if you had an intuitive explanation for why it's true.
What to say? Yeah, I think I do. How do I want to? Let's see. So I think the point here is the following. There are two essential ways to write down a complex number. One of them would be to write down a plus bi. So this is kind of giving you the rectangular coordinates of the complex number, a and then b, right? And here, this gives you a plus bi. This is the vector a comma b. But there's another nice coordinate system that we should consider instead, which is the polar coordinate system. Right? The polar coordinate system essentially should tell us that we should look for, what do I want to say? The polar coordinate system should tell us that we should be looking for complex numbers with a given argument and then scaling them by some real number. So here we would describe complex numbers as r times z, where the argument of z is the angle that z makes with the x-axis, the positive part of the x-axis, and the norm, or the size of the complex number, norm z is equal to 1. Where here the norm is going to be a plus bi times a minus bi. And then the way that we parameterize the unit circle is in terms of sines and cosines. So maybe one thing to remember is that we should be able to write a given number on the unit circle in terms of some constant a cosine of b plus sine of, like, in other words, if you want to parameterize the circle in R2, you do it as E1 cosine of theta plus E2 sine of theta, right? And then for a given choice of theta, that'll precisely give you some point on the unit circle. So essentially what we're doing is exactly this, where our E2 is now I. So this expression, E1 cosine of theta plus E2, or plus E2I sine theta, is a very natural expression to consider on one hand because it's a different way of expressing a particular complex number.
Okay, that makes sense.
As to why this should be equal to exponentiating something, I think that like the passage between this and e to the I theta has to be in terms of series. There's probably a different explanation that is a natural, like there's probably a good explanation, but none is coming to my head right now besides just look at the series involved and notice that the series for the exponential function is extremely closely related to the series for cosine and sine.
Okay.
But this was essentially my motivation for why you should expect cosine of theta plus I sine of theta to be a recognizable or a familiar quantity, that it should describe something nice, basically.
Yeah, that was the part that kind of tripped me up, is why does the
Why there are
exponential-
sines and cosines appearing.
Yeah.
So yeah, so I don't think I fully answered your question, but maybe I did answer why are sines and cosines coming up when I'm thinking about complex numbers.
Yeah, no, so that part is clear now.
Great.
All right. Well, thank you.
Yeah, absolutely.
Have a good one.
Yeah, have a nice afternoon. I'm happy to chat about these questions. Oh, shoot. I was recording this whole time.